Okay. Last but not least, we have Rui. That is going to tell us about the work at ByteDance on how to enable RDMA on virtual private cloud. Rui got his PhD from Drexel University, and he was working at ByteDance as a network engineer. But now he's actually part of the team of TeleAI, working on like new application for AI. So thank you so much.
Hello.
Yeah. Okay. Can we put the slides on, please? Okay, it's coming. Almost there.
So it's a PDF.
Sorry, but I love the LaTeX PDF. I mean, it's quite cool, I think. Okay, I think we are good to go. Yeah.
Okay. Hello, everyone. My name is Yuri Liu. I'm really glad to be here to present our work about enabling RDMA over and TCP over virtual private cloud. So I'm currently with TeleAI, but this work was completely conducted in ByteDance. So I presented this work on behalf of my former colleagues in ByteDance. I would like to start with background and motivation. So first, what is VPC? Okay, VPC is an isolated virtual network within a public cloud, and it closely resembles a traditional data center network. So tenants can create a VPC in overlay and manages the subnet and as well as instance within the VPC. Okay, so cloud providers have enriched the connectivity of VPC ever since the design of VPC. So now tenants are allowed to connect VPC with internet, with different VPCs, either inter-region or intra-region. And you can also connect VPC with local internet data center. Okay, so the problem is, so these are all TCPs because traditionally VPC only enables TCP. So interesting question to ask is, should we enable RDMA in VPC, and why should we do it? The reason behind this is that more and more applications will require RDMA or require both RDMA and TCP. And we are familiar with some of the applications, for example, the high performance computing, distributed machine learning training and storage. And some of them are quite relatively new to us. For example, a low latency live video streaming solution may require both RDMA and TCP at the same time. And a prefill decode disaggregate framework for LM inference may require RDMA TCP as well. So there will be more other such type of applications. So the primary goal of our paper is to enable RDMA over VPC and to better fulfill the needs of the tenants. We deem that the solution requirements should cover the following points. The first, the VPC RDMA, the performance of it should be close to physical RDMA, and it should be compatible with applications and intra-host RDMA optimization techniques. For requirement number two, we want a unified VPC supporting both RDMA and TCP rather than separate two overlays that support each of them. So to prime, we want a unified infrastructure which serves as a prerequisite of R2. So we choose Rocky V2 over InfiniBand and resulting in a unified Ethernet infrastructure. Okay, so when we start this project, we realized that there are several existing works on RDMA network virtualization. So we asked ourselves that can we simply incorporate those existing techniques into the VPC and solve our problem? The answer is no. The reason is that because all these RDMA network virtualizations are all based on interceptions. and which imply that they do not satisfy performance and or compatibility requirement. Let me explain this a little bit further. So in our paper, interception is defined as additional software, either in user space or kernel space, between applications call and the RNIC. So if you put software on the data path of the RDMA, then this will introduce a high latency overhead, which will cause performance issue. On the other hand, for the compatibility issue, the pure control path interception-based virtualization does not work for all QP types, such as unreliable datagram. And however, more than that, it's not clear how to co-deploy those interception-based virtualization with intra-host RDMA optimization techniques. So here are two examples. Okay, so the high-level idea is that these two examples are all based on interception within the intra-host. So given that the design space are overlapped, it's not clear how to co-deploy them. Okay, so let's move on to our approach. The high-level idea of our approach is to utilize VXLAN tunneling for RDMA virtualization. And this will have obviously two benefits. The first is for compatibility. VXLAN tunneling is interception-free and only depends on packet headers. This ensures VXLAN tunneling to be compatible with, say, any upper layer libraries, any intra-host interceptions, and any different type of QP types. And second, this sets up a foundation for unified VPC because VXLAN tunneling is already established for VPC's TCP stream. Okay, and we leverage SRLV and IOMMU as prerequisite techniques for our approach. So each VM, virtual function, is attached with a VNIC and is perceived as one PCIe device by the virtual machine. And this PCIe device will contain two interfaces, one for TCP and one for RDMA. Okay, so the overall architecture of our approach is like this. And we name our VNIC Jakiro because Jakiro is twin-head dragon, capable of spitting fire and ice at the same time. We name our VNIC Jakiro because we want to highlight the capability of our VNIC to send RDMA and TCP at the same time. Okay, so you can attach the Jakiro with your VM, and all its functionality, including VXLAN tunneling, are all implemented in the vSwitch data path. Okay, but VXLAN tunneling doesn't naturally solve everything. We need to solve several challenges to get the whole thing to work. So the first challenge is, how do we ensure bandwidth isolation for each Jakiro when TCP and RDMA coexist? So our initial idea is we can leverage congestion control by sending proper feedbacks at the receiver end. So this is how the solution goes. So we attach each Jakiro with a token bucket, and we set up the sailing rate of the token bucket to be equal to the predefined bandwidth of Jakiro. And once we detect a red tag, we initiate the back pressure signal. We do ECM marking for RDMA, and we drop packets for TCP. Okay, but the bad news is that this solution only works for the inter-bandwidth isolation. So within each VNIC, we are not able to control the ratio of RDMA and TCP when contention happens. Okay, so we realize that what we should do is try to ensure both intra and inter bandwidth isolation for each Jakiro when TCP and RDMA coexist. So to be more precise, intra bandwidth isolation means that we need to control the ratio of RDMA and TCP when contention happens. Beyond that, when there's no contention, we need to allow bandwidth borrowing between RDMA and TCP. Okay, so our solution was inspired by two classical ideas. The first is selective feedback, which was published in 1987. Okay, so unlike the standard AIMD mechanism, selective feedback only back pressures the greedy states or the greedy class when condition happens. Okay, another classical idea that inspired us is hierarchical token bucket for bandwidth sharing. Okay, so what we did is we removed the physical queues and token borrowing in the standard HTTP and combine that with selective feedback. And we end up with a method called distributed hierarchical token bucket, DHTB. And in DHTB, these token buckets act in an independent manner by just assigning, color tags to the packets. So those two leaf buckets will determine if the stream class surpass its predefined ratio, and the root bucket will determine if the condition happens or not. And we define the greedy state as yellow and red, and it will only back pressure the stream when it enters the greedy state. That's the whole thing. And because we have removed the token borrowing and the physical queues, this whole mechanism can be fully implemented in the hardware path of the RNIC. Okay, so we test the intra-Jakiro bandwidth isolation and compare our DHTB algorithm with the single bucket algorithm, and the results is like this. So when there's no contention, so both methods allows efficient bandwidth borrowing between RDMA and TCP, and when there is contention, DHTB will ensure that the both of the stream class converge to the predefined ratio, but STB fails to do that. Okay, so another challenge is we need to ensure RCQP quota control. So this is an illustrating experiment to show why we need to do that. So in this experiment, tenant A, the blue guy, acts as the attacker, and he keeps increasing his number of active RCQPs from 1K to, can I point that? Is there a pointer here? No. From 1K to 12K. And you can see when he does that, the throughput of all the tenants, including himself, drops. So that's why we need to perform RCQP isolation. So the question is how do we do that? Can we use VHCA manager? No, because it does not provide purely RCQP quota, and it is not flexible when for VMs with multiple VNICs. And another solution, possible choice is, can we do interception of the control verbs? The answer is no, because this may compromise compatibility. So our solution is an interception-free solution. We create a one-to-one map between RCQP and RC flow and solve the flow quota control problem. So the key idea is we leverage the fact that the virtual IP and the QP number act as a fingerprint for QP in a VPC. So if we define the set of these three tuple, this actually corresponds to the number of destined QPs that the VM1 connected with. So we use this three tuple to construct the RC flow table and manage the number of RC flow table. This will help us to control the number of RCQPs. And let's go back to this experiment. And when we launch the RCQP quota control, and we can see that the bandwidth stopped dropping, even if the attacker still keeps increasing his number of RCQPs from 1K to 12K. Okay. The last challenge is the performance of virtualized RDMA. So the rigorous performance requirement of RDMA necessitates offloading, but we cannot directly leverage the current offloading model. The problem is currently the model offloads a big hash table to the hardware path, and it has two problems. First is redundancy, and it will consume more hardware resources. The second is synchronization overhead. I will explain these two problems with this small example. So consider these two small tables, and then when we try to offload the corresponding big hash table to it, it's going to be like that. So you can see directly that this big table contains more table entries than the sum of these two small tables, which means redundancy. And to illustrate the synchronization overhead, let's consider the case when the blue entry of table A gets modified. And with the help of the color map, we know that those three blue entries in the big table needs to be updated. But the problem is such map is hard to implement in reality. So what we do instead is to full upcall all these flows to the software, and this increase the synchronization overhead. So our solution is try to offload 3 consecutive tables in the hardware, and will have 2 advantages. First, this will decrease redundancy, and second, we can do proactive update each time when there's a modification in the corresponding table in the slow path. Okay, so and we conduct experiments to compare these proactive updates with the full core updates. We can see that the conversion time is faster, and it also does not influence the innocent flows. And then we also compare the latency and the throughput of VPC RDMA with physical RDMA. We can see that the performance is really close. So the latency, the maximum latency, is under 1.28 microseconds for read, and the throughput is close to physical RDMA. That's probably all of my talk. Thank you for listening. I will take any questions.
Thank you so much for the fantastic talk. I know the coffee break has started, so maybe we have time for one quick question. Oh, there's a question there.
Hello, I have a question about the second. Yes. What if you have a turner that have two tags that he need to divide 1 QP to 2 QP? So you just can you you can just simply merge it into 1 QP. So is there any questions about?
What do you mean by 1 QP?
I think you decrease the QP to VIP and the desktop VIP. So if there need to be 2 QP in these 2 turnet, how you deal with it? Is this situation?
I'm sorry, what kind of situation is this?
Okay, maybe I would say, sorry, it's probably better if you just take this offline, just in the interest of time. Would that be okay? Because it seems it probably requires a bit more discussion.
Okay.
All right. Okay. Thank you so much. I just would like to thank the last speaker and all the speakers. And yeah, there is a coffee break, I think, in front of the auditorium.